want to calculate anything with it. But it is the same speed as before. It's the same L over D max speed that we talked about before, because it comes from the same thrust required curve, from the same, which is the same as the drag curve. So this, the minimum drag point is also the minimum thrust required curve, which basically means if I don't need a whole lot of thrust, I also don't have a whole lot of fuel flow. So for anything endurance, we want to suppress the fuel flow as much as possible, keep it as low as possible. So the minimum drag point is also our best endurance speed point for all practical purposes, and again it has the speed associated on the bottom. For maximum range, it's not as easy, similar to what we've seen with the climb angle and the rate of climb. Yes, we can minimize the fuel flow, but since the speed gets fairly low, we are not making a lot of distance with that fuel flow. So in general, our speed for max range will be higher than our max endurance airspeed, because we try to make more distance with a fairly acceptable fuel flow. So in general, we can accept a slightly higher fuel flow if it gives us a lot of change in velocity, and so it must be somewhere in this bottom part here of the curve, and it must be to the right side of where we're talking, and it gets pretty crowded here in our picture. I will erase some of the stuff here in a second, but in general we can expect it to be higher than our max endurance speed, and we can expect it here somewhere in the less curvy part of the curve down here on the bottom. To find it exactly, to go back with the book method of doing it, let me erase some of this stuff here. Actually, let me just drag some of the stuff out here. Gives me some space to work with. Alright, in general, when we're looking at the diagram, so the maximum range is obviously dependent on velocity we set, which is also part of the bottom of the curve here, because the faster we fly, the more distance we make. So what we're really looking at is exactly what it says here at the formula. Our maximum specific range can be accomplished whenever our fuel flow divided by our speed becomes minimal. So if we can get the highest velocity for the lowest fuel flow, or the combination of lowest fuel flow with the highest velocity outcome, which is basically what that quotient down here tells us. If we can get fuel flow divided by velocity to a minimum, then we're in good shape for making a lot of range. And that's basically what it says here on the bottom. In general, in any linear function, we know that the most simple linear functions are the ones which go through the origin of a diagram, and they have a certain slope on their curve, and the slope of the curve is basically whatever the change in, or the delta in y is, over the change of the delta in x here. That's the slope of the curve. We have the same relationship basically here. We've got the fuel flow. We said the thrust required is the same as calling it fuel flow. So we've got the fuel flow on the left, and we've got the velocity on the right, and we set the change in y over the change in x is basically what dictates the slope of the curve, and we want to minimize that. So that one should be minimal, and one should go down as much as we can. Then our fuel flow over our velocity should also go down as much as we can, which directly tells us we can actually express that relationship between fuel flow and velocity in our diagram here with any curve that goes through the origin. So this curve here would be a relationship between fuel flow and velocity, and what we try to do graphically is we want to shift this curve down as far as we can. We want to get that slope of the curve as low as we can. So we want to make it as flat as we can, possibly. However, we are limited. We can't just shift it down and call it good. For example, we can't just put the fuel flow to velocity curve in here, because yes, this would be an awesome range relationship between velocity and fuel flow. However, it's not part of our actual aircraft, because our actual aircraft is still given by our curve here. So while we try to shift it down, we still have to be somewhere intercepting our curve with the real aircraft graphically here. So we can only shift it down as much till it starts leaving the curve, or more precisely till it becomes a tangent on our curve. That's how far we can shift it down. Sorry, I want to give you that in a more precise penciled way here. One more time. So if we shift that curve down, at some point it becomes a tangent on the curve, and that's as far as we can go, because if we shift it any further down, we're not touching our curve anymore, so we don't have anything to do with the real aircraft anymore. It would be nice, but it isn't, or it is not workable. So the lowest we can get that slope to go, that fuel flow over velocity min, that's basically what it is a tangent that we draw on our thrust required curve. And based on that tangent, there's an intercept point here somewhere. You can do it more precisely than I can do it here, but from that intercept point you can read an associated speed, and then obviously also an associated thrust required for that thing. But that speed will be your max range airspeed for that aircraft based on your thrust required curve. Again, it's a graphical solution. I just want you mathematically to understand where that tangent solution comes from, which is basically the trying to minimize the ratio between fuel flow and velocity here, which is the same as saying we try to kick the slope of any tangent going through the origin, or any line going through the origin, any linear function through the origin. We try to get the slope as low as possible. But still intercepting our actual curve, our thrust required curve, because that's obviously one condition that we have to fulfill. We still have to find a solution that is part of our actual aircraft and is flyable by our actual aircraft. So that's the graphical solution for finding the max range airspeed. Again, going backwards through the different assignments: max range airspeed, build a tangent on your curve, find the intercept point that gives you the speed. Max endurance, we said, has to do directly with the fuel flow being the same, or being proportionate to thrust required. Therefore, if we can minimize the thrust required, then we're in good shape for our minimum fuel flow too, which gives us the maximum endurance. So again, the minimum for the curve will give us also the minimum, maximum endurance. Maximum flying speed, we talked about that in the beginning somewhat. Whenever we are having a thrust required that is bigger than our thrust available, then we are like outside the envelope of what the aircraft can fly. So the intercept point between thrust available and thrust required is basically the maximum, the fastest we can go. Anything faster than that will fall outside, will require more thrust than we have available, and therefore is not flyable. So this one becomes the maximum speed we can fly. Rate of climb. For any given speed, we want to find the difference between thrust available and thrust required, and that difference in thrust available versus thrust required goes into our rate of climb formula together with the speed at which it happens. If the speed is given, then obviously that speed goes in there for that one. And for climb angle, again, same principle. We find whatever speed we are looking at, 400 knots for example, looking at thrust required and thrust available, building the difference between the two, and that difference goes into our climb angle formula. And then if we were to find, it's not part of your assignment, but if we were to find the maximum climb angle, we are again at the minimum point here, because that gives us the biggest difference between thrust available and thrust required. And those are, in short, all 4 assignment parts. The long explanation was at the beginning, here the short summary. One last thing I wanted to touch on, that's also touched on in the book, and that's important to notice for the final exam work, is the changes. When you read through the book assignment, take a good look at those different changes. So how do those performance parameters we just talked about change with altitude? How do they change with the speed, with the configuration? So changes in altitude, changes in configuration, and changes in weight, which are the 3 main ones, and then there's also change in wind, which might influence it. But those 3 are the main underlying things here. The big things to notice in those are common relationships. For example, if we are talking effects of altitude on thrust available and thrust required curve, we will notice that it is basically coming from the change in sigma that shifts the whole curve, all the curves, all the thrust required curves basically towards the right on our true airspeed scale. On equivalent airspeed scale there wouldn't be any difference, the curve wouldn't shift at all, but on the true airspeed scale we basically, that's exactly what it is. The equivalent airspeed calculation is giving us the new true airspeed where the curve ends up being. So the thrust required curve shifts by that exact same relationship that we know from module 2, which is the relationship between true airspeed and equivalent airspeed, which is by the square root of sigma here, or inversely proportionate to the square root of sigma. And that basically goes in here, and that's all you have to do, or all that happens there is graphically the curve shifts by exactly that amount. That is the conversion from true airspeed into equivalent airspeed. The other thing that happens is that, and we talked about that earlier already, that our thrust available curve will come down. In general, again, it's pretty much straight line curves, but our straight line will be at a lower level the higher we go in altitude, because the thrust output of our engines will be reduced based on density as well. Similarly, for configuration change, we notice that the biggest influence is parasite drag. So we see a lot of difference here on the right side of the curve. There's a huge shift from one configuration to a higher drag configuration on the parasite side of the curve, while on the induced side the shifts are relatively small. So in general the curve on the left has the same, almost the same stall region of intercept, but then the further we go to the right, the more influence the parasite drag has, the more we will see a difference between the curves basically happening. And then for weight change it's the opposite. On the high speed side the weight is not doing a whole lot of difference, but on the slow speed side our induced drag with a higher weight aircraft becomes obviously higher, and therefore our curve here shifts up on that side, because we obviously have much more drag, much more induced drag with a higher weighing aircraft. So those basic relationships, you don't have to put it numerical, but just understanding how those work and how they play out graphically for your curves is basically what I want you to take out of the discussions in the book there when you go through those. Alright, let me just recap real quick whether I forgot one here. No, we talked about that. Alright. And that's all I've got for the first third of your assignment. And I will head over into the prop in just a second here. See you back soon.